It's in the outer shell, which is the first shell. It's in the s orbital, so it's in a 1s orbital. And what was the shape of that 1s orbital? Who remembers?
Tennis ball.
Tennis ball, sphere. Okay, so I got a 1s orbital here and a 1s orbital here, and each of them have one electron in them. If I bring the two hydrogens close together, watch what happens to the 1s orbitals. You see how they overlap with each other. And so now it's technically possible for both electrons to exist in both 1s orbitals at the same time. So basically what we're saying here is that the picture becomes something like this. This guy has its 1s orbital, this guy has his 1s orbital, and where they overlap, the electrons could coexist. And so it's like a trick. It's a con game, and we interview the guy on the left and say, well, how many electrons do you have? And what does he say?
2.
I've got 2. And if we interview the guy on the right, he says, I've got 2. They both think they have 2 electrons. And that illusion will continue to happen as long as what? We keep the hydrogens together. And so that desire to stay together so that they have this happy situation. And remember, what does happy situation translate into? The energy goes down. It's an energetically favorable arrangement when they do this. The energy of the system drops, and they say, ooh, we like lowest possible energy. And so we'll stay together to assure that that energy stays as low as possible. And since they're not transferring electrons like we saw in the ionic bond case, they are literally sharing electrons. This is a different type of bonding, and we call it covalent bonding. So covalent bonding is when 2 atoms will share electrons rather than transfer the electrons from one to the other. Now, this doesn't have to happen with identical elements, although it does happen with identical elements 7 times. There are 7 elements in the table that will form what are called diatomic molecules. And so it's to our advantage, a little later on, to know what those 7 elements are. And we have a simple way of remembering them. The 7 elements are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. What this means is that these 7 guys all occur in nature as 2. Fluorine, F2, nitrogen, N2, oxygen, O2. And how can I remember that? If you remember the word Hunkelbrief, right? Just read it, Hunkelbrief, boom, you know the 7. Hunkelbrief. Okay?
You said these are diatomic.
Diatomic molecules. So they all occur as 2s. Now, they don't have to be the same. Could I perhaps make a molecule with hydrogen? How many valence electrons?
2.
1. And chlorine, how many valence electrons?
6.
Oh, 7.
It's 7, okay? It's in group 7 of the periodic. So, 1, 2, 3, 4, 5, 6, 7. Okay? You can pretty much guess what I'm going to do here. I'm going to push that hydrogen over and look at the sharing that takes place. It's a beautiful thing. They're sharing electrons. And the hydrogen believes it has 2. The chlorine believes it has 8. And they're happy. They're happy.
So he's not giving it away so he can become neutral and chlorine can become neutral as well.
Okay, time out. If he gives it away, he wouldn't be neutral. If he gave it away, he would be a positively charged ion. Okay? Because he was neutral when he had it. So in this case, they opt to share. It's a bit of a bad example because you could view this in terms of the plus and minuses, but don't. Think of this as sharing, okay, for the moment.
So all of those can pair together to form like one thing
Who?
that all of those were like.
No, what Honkelbrief means is to pick any one. Pick one.
Oxygen.
Oxygen, in nature it occurs as O2.
Okay.
That's what that means. Pick another.
Cl.
Cl, in nature it occurs as Cl2.
So if we were to like draw these, they would all match up to where they would share the 2 electrons or whatever. Like,
Yes,
Can you do another example?
yes. Well, let's pick on chlorine. How many valence electrons?
7.
Okay, if I bring in another chlorine, how many valence electrons would it have?
Okay, yeah, that's what I was talking about.
What the what? Okay, there's my picture. Does each chlorine have an octet?
Yes.
Match made in heaven. Now, let me ask you this. Did I have to use a chlorine here? Maybe that's what you're alluding to. Could I use a fluorine?
Yes.
How many valence electrons does fluorine have?
7.
See, I shouldn't have erased all those X's. I could have just erased the
CL.
Cl and put the F in there. Is that a match made in heaven?
Mhm.
Yeah.
So it's
Do like bromine too, so yeah.
I could do bromine. I could do iodine. Let's stop there.
Okay, yeah, I got it.
Okay, let's not get too crazy yet because there are some things that happen as we go along. Yeah.
So that would be chlorine 4. No.
Not a +2. It is the subscript that tells me that I have 2 atoms in the molecule.
So would that be chlorine fluoride?
Yeah, something like that. Okay. Gets a little sticky when you're using both non-metals.
Is that still considered a diatomic molecule?
It is a diatomic. It's not a homonuclear diatomic. These are all homonuclear, which means they have the same nucleus. They have the same atom. These are heteronuclear diatomics. And there's a bunch of these. Many more than 7. Okay, yeah.
What's homonuclear again? They have the same.
It'd be the same atom. So Cl, Cl.
Thank you.
Now, these 2 different types of bonding that we're laying out here, we've got a good hold on ionic bonding. We know how to write ionic compounds, we know how to make them and name them and all that. And now we've introduced covalent bonding. We've got a little bit more to say about this, but we get the general idea that it's the sharing, the kumbaya sharing of electrons here that are going to create this type of bonding. These different bonding styles lead to different types of chemical substances. Ionic bonding logically leads to ionic substances. And I think I've already mentioned to you that ionic substances tend to form crystal lattices. How many people went home and looked at a piece of sodium chloride, a piece of table salt? Not very many. And what'd you find? All right, I'm going to steal some salt from the cafeteria, bring it in next Tuesday. We'll do an in-class exercise of looking at salt. Okay. These are ionic materials, and they form between very dissimilar elements. You should have the sense now that ionic materials are generally made from a metal and a non-metal, or a metal and a polyatomic ion, which acts like a non-metal. So we see dissimilar elements that are forming the chemical substances here. Covalent bonds are going to be made from substances that are relatively similar to one another. Look at chlorine and fluorine. Where do they appear in the periodic table? Well, they're in the same family of the periodic table. They're right there. Okay? So there's similarities between the elements when they share electrons. Ionic bonding results from a transfer of an electron. Covalent bonding is a sharing of the electron. Ionic compounds form crystal lattices. And these things have usually very high melting points and boiling points. How can you melt salt? Have you ever tried to melt salt on your kitchen stove? It's not going to work. You have to get to almost 1,000 degrees centigrade to actually melt salt, and your kitchen stove is not going to get that high. And so ionic materials, very, very high types of melting points and boiling points. Covalent substances, on the contrary, tend to have low melting points and boiling points. They tend to sometimes be liquids or gases at room temperature. There are no ionic materials that would be a gas at room temperature.
What did you say about the ionic? They were crystal what?
Crystal lattice. They form that very ordered structure, okay, which is what we were trying to look for in the salt.
You said the covalent bonds are more gases than liquids?
The covalent bonded compounds tend to be more gases, liquids, or solids that will melt at relatively low temperatures. Now, for putting together covalent bonded compounds, the dot structures that we looked at a little bit earlier, and then remember we decided, well, the dot structures for ionic compounds weren't the best way to do it. It was a much better approach to look at the charges, the pluses and the minuses, and make sure that they balance with each other. In the case of covalent compounds, the dot structures are a pretty good bet as to what to use. And so if we're starting to piece them together, we have some good examples on the board already. We've got H2, or hydrogen and hydrogen, sharing electrons. We've got an HCl, where the hydrogen and the chlorine are sharing electrons. We've got a chlorine and a fluorine, and we had chlorine and chlorine up here sharing these electrons. And so these dot pictures become pretty good and valuable tools for us. Now, in this kind of a picture, where the electrons that are literally being shared between the two elements, those are called bonding electrons. The ones that are scattered around simply completing the octet, like these over here, these are called non-bonding electrons. Sometimes we call a non-bonding electron a lone pair of electrons. Lone pair. And that's probably the more frequent term, although non-bonding is perfectly correct. Now, one of the things we can do with these dot structures is that we can begin to predict the number of bonds that something is likely to involve itself in. Let's look at a hydrogen. Hydrogen has one electron. Now, hydrogen's an exception to just about everything we do. Hydrogen's an exception. He doesn't have an octet rule. He's got a duet rule. He only needs two. Why is that? Because in the first energy level, there are no p orbitals. There's only an s. And so we achieve the electron configuration gas of helium with just two electrons. So hydrogen's a special guy. All right? But if that's the case, then how many electrons will he always want to share? Just one. And that means one bond. So if he's bonding with himself, look, there's one bond there. If he's bonding with a chlorine, there's one bond there. If he's going to bond with a much larger carbon compound, he'll have only one bond available to him. Now, if we take something like chlorine, chlorine has how many valence electrons? 7. Look at that picture. How many electrons does it need to share to complete its octet? Consequently, how many bonds do you think chlorine will be involved in most of the time? Just one. Chlorine's a one bonder. On the other hand, let's look at oxygen. How many valence electrons does oxygen have? 6. How'd you know that? It's in group 6 of the periodic table. So I'm going to put them around one at a time until I'm forced to pair them up, yada, yada, yada. To get an octet of electrons, how many electrons will the oxygen need to share? It's going to be involved in 2 bonds. Okay? It's going to be a 2-bonder. Let's go to carbon. How many valence electrons? 5. 4. Trouble with Roman numerals, huh? 4. So how many bonds will a carbon have? 4. This is a golden rule for Chemistry 1152. If you're planning to take a Chemistry 1152, on the first day, what you will do is be instructed to get a tattoo on your arm that says carbon has and must have 4 bonds. It is the golden rule in Chemistry 1152. Basically, if you can count to 4, you can pass that class. Okay. Oh, okay, there's a little bit more than that. All right, so carbon is a 4 bonder. So we can start to look and see what kind of bonding would any particular atom like to be involved in order to complete its octet. So let's go back to oxygen, and let's pair them up with something else. Like, what if I paired them up with hydrogen? How many hydrogens would I need in order to come in there and supply the 2 electrons that oxygen is demanding? 2. And so I put one here and one here, and look, I have a beautiful chemical compound. Are the hydrogens happy?
Yes.
They each have a duet. Is the oxygen happy?
Yes.
It's got an octet. What is this? It's my favorite molecule. Okay, that's on a quiz at the end of the semester, by the way. My favorite molecule is water. And so we have this molecule. Could water be H3O?
No.
Understand this. You've known water was H2O since you were a little kid, before you came into this class. But today, you truly understand why it's H2O. It could not be H3O. It could not be HO, because the bonding would not be satisfied. And we can't have unhappy atoms running around. The world would be all amok. Right? So we can't have that. So let's try another one. How about nitrogen and fluorine? Let's see if we can piece those together. They're both nonmetals, so we're talking covalent bonding over here, sharing of electrons. Let's pick one guy to start with, maybe the guy on the left. Nitrogen, good choice. How many valence electrons?
5.
So I'm going to put them around, 1, 2, 3, 4, 5. And so how many electrons does the nitrogen need to achieve its octet? 3. It's going to be a 3 bonder. So fluorine, how many valence electrons?
7.
How many bonds will it be involved in?
1.
So logic tells me how many fluorines am I going to need here? And so we can put them in here one at a time. There's, I'll just use little dots. There's 1. Fluorine's got a 7. Another one. And another one. Look at that picture. It almost gives you goosebumps to look at that picture and say, oh my God, that's just aesthetically beautiful. That every nitrogen, or the nitrogen, has 8 electrons. Every fluorine has 8 electrons. This is octet heaven. And this molecule is the way this should exist. Would it be NF4? No.
Is that why they put them in the shapes whenever they do molecule dioramas, like with the little balls?
Let's not do shapes yet.
Oh, okay.
It's a whole other topic we have to come up to yet. In this chapter, by the way. But I need a little more ammunition before we go there. Okay. Other questions? All right, let's try the game backwards. We can take a nitrogen, we can take the fluorines, we can figure out how many fluorines to put together. Say with oxygen and hydrogen. How about the air we breathe? What's the main component in the air we breathe? Actually, the main component is nitrogen, but what's the important component? Oxygen. And what is it chemically? It's O2. All right? So there's the stuff we're breathing. Let's see if we can do a dot structure of O2. Knowing the formula, can we come up with the dot structure for this? What do you suggest we start with? An oxygen. Good choice. That's all we've got. How many valence electrons?
6.
6. So 1, 2, 3, 4, 5, 6. All right. What do you think I should try to pair up with this? Another oxygen. How many valence electrons would he have?
6.
So 1, 2, 3, 4, 5, 6. Okay, good. Is that a beautiful picture?
No.
Why? What's wrong?
Neither have an octet.
I don't have an octet. Neither oxygen has an octet. They have 7. Now, how can I fix that? Oh, here's an easy way. I'll bring in some hydrogens. They each have 1. Ta-da! Do the oxygens have octets now? Is this a good molecule? Yes, it certainly is. It should exist. It does. It's called hydrogen peroxide. But is it O2? No. So if I want truly to make O2, I can't just bring in some other element to fill in the gaps. I have to find another way. And the other way here, the only other way here, is to come to the conclusion that the oxygens are going to share 2 pairs of electrons. They're not only going to share electrons here, but they're going to take these guys and share them like this.
That would be like a double bond. That's a double bond.
Yes, I can do that. That is a double bond. In general, we would call it a multiple bond. Specifically here, a double bond, because it's 2 pairs of electrons. So what that means is, we've got a definition. A covalent chemical bond is a pair of electrons. A double bond would be 2 pairs of electrons. Okay, I'm going out on a limb here. A triple bond would be 3 pairs of electrons. What a class. Now, does this work? In other words, does this guy think he has an octet? Yeah, he does. Does this guy think he has an octet? Yes, he does. Now, we might draw this like this. Simply because we tend to do that sort of thing here. We would draw it like this. And understandably, what does that bond or dash mean?
Single,
A pair of electrons. What does 2 dashes mean?
double bond.
2 pairs of electrons. Oh, give us one. All right, the other component of air that we mentioned is nitrogen. N2. Both oxygen and nitrogen are Hunklebriffs. Okay? Can you draw me the dot structure for N2? Go. 12 seconds.
Does it have to be a single or double?
What? Those are single. You do what you have to do to get N2. N2. Okay, does putting them together with a single bond work?
No.
No. But if I move this electron and this electron over, does that work?
No.
But if I move this one and this one over, does that work?
Yes.
Aha! And what do I have? Triple bond. Like so. Now this doesn't have to happen just between 2 elements that are the same. Let's try carbon and oxygen. How many valence electrons does carbon have?
4.
1, 2, 3, 4. Oxygen.
6.
Let me bring in an oxygen here. So 1, 2, 3, 4, 5, 6. And another oxygen. 1, 2, 3, 4, 5, 6. Okay, is that working for us? No, look closely. The oxygen here has 7. The carbon is only 6. This oxygen, 7. So what I have to do is this. Now, look at this oxygen. How many? 8. Carbon. 8. Oxygen. 8. And so I have a molecule that looks like this. We know it as carbon dioxide. Now, there are some other things that can happen. We can create what's called a coordinate covalent bond. We've already done this. I didn't call it that when we did it. But let me show you using another molecule. I can draw a dot structure for this molecule. It's not a particularly appealing dot structure, but it's one that we can play with. I'm sorry, this is wrong. No, it's not. Coordinate covalent. No, I'm right. Okay.
But there's 2 oxygen.
I know. Okay, why is this not appealing to us?
Too much triangles.
No hydrogen.
You don't like my triangle? All right, this guy is forming a bond, but he's not contributing anything to the bond. He is simply taking advantage of the lone pair of electrons that were sitting here. This happens in chemistry. I don't think we'll go beyond this right now. We won't pursue this. But this happens in chemistry. And when it does, this bond is given the name coordinate covalent. And it simply means that a bond has been made, but one atom has supplied both of the electrons for the bond. We saw it in the formation of the ammonium ion. Remember when I took ammonia and brought in a hydrogen ion to sit on the lone pair of electrons of the nitrogen, and we formed our first polyatomic ion, the ammonium ion. And so it happened.
Can you say what it was again?
It's a coordinate covalent.
I mean, a bond is made of what else?
A bond is made between 2 atoms, and the bond electrons come from one of the atoms. Now, doing dot structures in general can be complicated. And so what we have is we have a stepwise procedure that we can follow to do some of the more complicated dot structures. So on Tuesday, what we'll do is look at that. Now, after that, we're going to get into something called molecular shapes. So I think it's important that you would go ahead and read the end of chapter 4. You're not going to be pleased with it. You're not going to be happy. You're not going to understand it. But read it once or twice to get a feel for it, so that when we talk about it, some of those things will be clarified as we go along. Also, are we planning to meet Monday
Yes.
at 11? So if anybody's interested in that group that meets on Monday at 11 down in the UC Atrium, out by Pizza Hut, you're welcome to join them.